Chapter 2, Protecting the Ozone Layer, Part 2, Chemistry and Context. We're going to be talking about waves of light and electromagnetic radiation and matter. Let's take a look at some videos on light, and then we'll talk about the key information. So light is defined by the wavelength and the frequency. The wavelength is the distance either peak to peak or trough to trough in the wave itself. One cycle is also defined by one wavelength. Frequency is really the number of cycles per second, but when you see the units of frequency, really they're just per second. Sometimes you might see that written either s to the -1 or second to the -1. Really that's just saying per second, like you would see miles per hour. Longer wavelengths have a lower number of cycles that pass any given point per second, so they have a lower frequency and low energy. Shorter wavelengths have a higher frequency and higher energy. Frequency is the number of waves that pass a fixed point in 1 second, as I just talked about the units up here. The electromagnetic spectrum covers light in all its forms. Light, what we see on a day-to-day basis, what our eyes can perceive, is called the visible region of the electromagnetic spectrum. We can only see just a select number of wavelengths of light, but there are many other types of light that we cannot see. We can hear radio waves. That in a way is, I wouldn't call it light, but that is in essence the same creature we're talking about when we talk about visible light. It just has much longer wavelengths. And then on the other side we have gamma rays, which have very, very short wavelengths and are very, very high energy. So we perceive this type of radiation, this quote-unquote light, differently, but really they only differ by the wavelength and frequency. This little symbol represents frequency. It's a Greek nu. It looks a lot like a V, but really it's a nu. The symbol nu. To remember the visible wavelength, people sometimes use the abbreviation Roy G Biv. It's backwards here, but red is lowest in energy, then orange, then yellow, then green, then blue, then indigo, and violet is highest in energy, or shortest in wavelength. One additional aspect to light I'd like to point out is that it always moves at the speed of light, irregardless of the wavelength or frequency. And the wavelength and the frequency, if you multiply the two values together, you will end up with a constant. And that constant is roughly 3 times 10 to the 8th meters per second, or the speed of light. So you could, if we're given the wavelength, figure out the frequency. Just divide the speed of light by the wavelength in meters, making sure to keep your units consistent. Or if you were given the frequency, you could divide the speed of light by the frequency to obtain the wavelength. So a Thinker Buddy question. Which statement comparing these two waves in the electromagnetic spectrum is correct? Wave 1 has a blank wavelength, blank frequency, and travels at the blank forward speed as wave 2. A, longer wavelength, lower frequency, same speed. B, longer wavelength, lower frequency, and faster speed. C, shorter wavelength, higher frequency, and same speed. Or D, shorter wavelength, higher frequency, and slower speed. The answer is C. Remember, wavelength is defined as peak to peak, so this distance here is less than this distance here. Okay, so it has a shorter wavelength. I could have measured it from above as well. Shorter wavelength, it has a higher frequency because if the wavelength is shorter, then one cycle will pass a given point. If I say this point here, one cycle will pass this point, or more cycles, I should say, will pass this point per given second, because all light travels at the same speed. It all travels at that constant c, the 3.0 times 10 to the 8th meters. Let's get that point there. Meters per second. Now, as far as what type of light in the electromagnetic spectrum reaches Earth, a little bit is ultraviolet. A fair amount is visible light. And the remainder of the light is, or the majority I should say, is infrared, is the infrared portion of the electromagnetic spectrum, which is slightly less energy, longer wavelengths. Here on the x-axis we have wavelength in nanometers. Okay, and for every 1 meter we have 1 times 10 to the 9th nanometers. So nanometers are very tiny. Very tiny. These waves of light are extremely small. So these wavelengths are getting larger. Remember, longer wavelengths, lower energy. And it's the UV radiation that we have to worry about when we're concerned about perhaps a sunburn. That's the high energy radiation. Okay, now let's try to answer the question, how many nanometers are on 1 times 10 to the minus 5 kilometer using the techniques from the video? And we're given a couple pieces of information that 1,000 meters are in 1 kilometer, and there's 1 times 10 to the 9th nanometers in 1 meter. Okay, so hopefully you spent a little time trying to solve that problem. So we started out with 1 times 10 to the minus 5 kilometers. And we're given 2 equality statements to get to nanometers. So first thing I need to do is I need to put the unit down here that will cancel my unit up here, because I'm trying to get rid of kilometers. I don't want my answer in kilometers. I want my answer in nanometers. So I'm going to put 1 kilometer down there to give me meters. up here. I'm just rewriting this equality statement, bringing that down there and that up there. If it suited me, I could have written 1 kilometer over 1,000 meters. We could also convert that equality statement into something that looks like this, but what would be the problem with that? If I had written it like this, I couldn't cancel kilometers. So now I somehow need to end up with nanometers. In order to end up with nanometers, they have to be up here in the numerator when my problem ends. So that means when I use this equality statement, I need to have meters down here and 1 times 10 to the 9th nanometers up there. And when you do that, meters cancels. And so you have 10 to the minus 5th times 10 to the 3rd times 10 to the 9th. So we should end up with 1 times 10 to the 7th. So now we're going to take a look at another video exploring the strange properties of light, known as wave-particle duality. Okay, so as you saw in the video, we can look at light as packets of energy called photons. Those photons have an energy that can be described using this formula here, where E stands for energy, the H stands for a constant, and this little symbol here is a nu, if you recall, which stands for frequency. So H is a constant, funky looking constant. But if we multiply that constant by the frequency of light we're working with, we obtain a value for energy. And we refer to energy in a unit called the joule. And this way, based on the light's energy, we can relate it to the frequency and vice versa. The higher the frequency, the shorter the wavelength, and the higher the energy. So here's another picture of the electromagnetic spectrum. And you could see going right to left, we have increasing energy. As the wavelength gets shorter and shorter, the energy gets greater and greater. And down here on this side is gamma rays and X-rays and ultraviolet radiation. And you know X-rays, when a doctor or a nurse or someone in the medical profession is taking an X-ray, they always go hide behind a large wall, generally speaking, or they're covered in lead, because those types of light rays or electromagnetic radiation is very high energy. And it's for this reason that we have to be very careful and protect ourselves from ultraviolet rays. They're high energy rays of the electromagnetic spectrum. And they can actually break bonds. If you see this little coils representing a bond between two atoms, if ultraviolet energy strikes it, it will actually break that bond. So it can actually damage the bonds between the atoms in our body or in plant life. This ends Chapter 2, Part 2.